So yeah, I'm Sean Glover. I work at a company called Epica. I've organized a few of these meetups. This is my first presentation. It's on Spark, Apache Spark. I'm going to briefly talk about what Spark is and contrast it to some of its predecessor technologies. We'll also discuss Spark as a driver application and how you can plug it into cluster environments such as the Hadoop 2.x ecosystem, as well as Mesos, Apache Mesos. So I'm curious how many people here have used Hadoop before, MapReduce? Okay. How about Spark? Okay. So I don't do this at my day job. I just picked this up about a month and a half ago. So be gentle with your criticism, because I know there's a lot of big data heads in the room. So I like practical talks. So I'm gonna cap off, or the latter half of this talk is going to be mostly practical stuff. I'm going to show you some code actually running, both on a single machine and on a small cluster. So hopefully everything goes to plan. So disclaimer, I'm not a data engineer or a scientist. So why am I giving a presentation on Spark? Well, like I'm a generalist. I consider myself full stack. Hadoop and now Spark have always been interesting to me, and I figured the best way to motivate me to learn these technologies, or one way anyway, was to do a talk on it. So here I am. This comic is asking the question, the data scientist needs to really ask why they're getting the data they're getting, instead of just going out there and trying a bunch of new technologies, or iterating over some data and seeing how awesome it is. Like, you have to have that fundamental question as to why are you doing what you're doing. So start with some kind of business rationale. That's what this comic's describing. It doesn't really jive with my spiel at the beginning, but anyways, I thought it was funny. So what is Spark? Apache Spark is a general purpose computing engine for large-scale data processing. It was written in Scala. It runs on the JVM. The core component of Spark is this thing called the RDD, the Resilient Distributed Dataset. And there's a really good paper that introduced Spark to the community. I think it was in 2011. It's from Berkeley, some researchers at Berkeley, and it defines an RDD as a resilient distributed data set is a read-only collection of objects partitioned across a set of machines that can be rebuilt if a partition is lost. So that's a really cool thing about RDDs, is how they respond to failure. For example, if one node in the cluster dies, the solution they chose is something known as lineage. So lineage, as defined by that Berkeley paper, is the elements of an RDD need not exist in physical storage. Instead, a handle to an RDD contains enough information to compute it, starting from the data in reliable storage. This means that they can always be reconstructed if nodes fail. So instead of like a model like HDFS, where you replicate chunks of data across different nodes, Spark took the approach of recomputing that data. If you have a cluster of Spark nodes and some of that data was in memory in one of them and it blew up, and you have a need for that data all of a sudden, it can be recomputed based on the data you started with, and then just kind of iterate over all the data flow you used to reconstitute it. It's pretty neat. Again, from the Berkeley paper, RDDs achieve fault tolerance through the notion of lineage. If a partition in a RDD is lost, it has enough information about how it was derived from other RDDs to be able to rebuild just that partition. What else I got here? Oops, where did this go? Sorry. Another interesting thing about Spark is the API support. So obviously it was written in Scala. Scala is kind of first-class language to them. The API is really awesome. It plugs into the Scala collections API. So you iterate over, you create your pipelines just like you would in-memory pipeline using the collections API. So you can use the actual map and the reduce and the group by, filter, higher order functions. Something I was alluding to earlier, after each step in the data flow, the intermediate data is stored across a distributed memory store. I'll talk a bit more about that later. You can play with Spark, the whole cluster, in a modified Scala REPL. So if you've used the REPL in Scala, it's basically the same REPL enhanced for working with a cluster, and you can inject some of your own compiled artifacts into that and get access to them, and really just mess around like you would in a normal Scala REPL, but now you have this whole cluster of machines at your disposal. So Spark is the first, at least the paper makes this claim, that Spark is the first system to allow an efficient general purpose programming language to be used interactively to process large data sets on the cluster. And then this short little image, I took a screenshot. We're actually at version 1.3.0, and there's a pile of log lines below it before you actually see the Scala REPL, but I wanted to get the ASCII art in there. So it's a lot like MapReduce. It effectively is MapReduce. It's kind of like 2.0 MapReduce. It's different from it in a few different ways. Iterative jobs. So again, from the Berkeley paper, they say many common machine learning algorithms apply a function repeatedly to the same data set to optimize a parameter. To implement these algorithms in Hadoop, you're forced to dump to disk and then reread your data between reduced steps. Spark keeps this data in memory, distributed memory, which obviously has an enormous performance increase if you have a non-trivial data flow. And generally you do. You have many steps in your data flow. Another way it's different is with its interactive analysis. Again, I keep going back to the Berkeley paper because it says it way better than I could ever articulate it. Hadoop is often used to perform ad hoc exploratory queries on big data sets through SQL interfaces like Pig and Hive. Ideally, a user would be able to load a data set of interest into memory across a number of machines and then query it repeatedly. However, with Hadoop, each query incurs significant latency in the order of tens of seconds or more because it runs as a separate MapReduce job and reads data from the disk. So Spark allows you to temporarily persist, or in the API it's called cache, a transformation or reduction to memory, and then you can use it later in your driver application. So you can go so far in your data flow and then say, okay, I want to reuse this data for other steps. Let me cache it, or suggest Spark cache it in their distributed memory store, and then you can go back to it and reuse that data. And since it's in memory, those subsequent operations will be really fast. Finally, the big difference between using MapReduce framework and Spark is that you can write it in Scala. So it allows you to write a lot less code than is typical on the Hadoop MapReduce framework. So a Spark driver application, this is kind of like the your main method. It has like, it's an object. You have a main method. You do your operations. The heart of a Spark driver application is the Spark context. It contains all the information required for your application to run. You can configure Spark context with environment variables. They have a Spark defaults XML config file through the command line interface through these helper scripts, Spark Shell and Spark Submit. Spark Shell is the one that spins up a REPL. Spark Submit is more of a production kind of script where you put the job onto your cluster. Spark context is singleton, so you can only have one per JVM process. This makes testing a little easier to do because it's easy to change your master resource manager. So in a testing scenario, you can test your app against your local machine. You might just have access to one core or whatever, and you have to run it in serial, unfortunately, because it's singleton. But it's nice that you can swap out the resource manager you're using from just an in JVM process resource manager to something you use in production, which would point to an actual cluster. So testing is pretty easy in Spark. Okay, what else? Data sources. So data sources, the Spark context supports out of the box our local file system, HDFS. You can even stream from HTTP somehow. I haven't done that. It's pretty common to utilize HDFS for Spark application I/O. There's also a Spark streaming project, which isn't part of the core package, but it lets you stream from a number of different sources, like Twitter and like a more conventional web stream, generic HTTP stream. And this is ripped off from Spark's documentation itself. This is a very simple Spark application. So all it's doing here is it's doing some imports. It's instantiating a Spark context, and it's loading in the README file as the source data. And what it's doing is it's going over. Before that, it does this cache operation, which is what I was talking about before. This will cache it in the cluster or whatever your resource manager happens to be. And this is important because there's two operations here. One that's counting lines that contain the letter A, and one that contains D. So the operation count actually kind of flushes the job. There's one of the ways you can flush a job. So count will load this data set into memory and return a count. And then when you get to B, that data set will already be in the memory. So that subsequent operation will be a lot faster. So for the practical demo that I'm going to show you, I used the Stack Exchange data set. Colleague of mine, or ex-colleague, suggested it to me. He couldn't make it tonight, but every quarter the Stack Exchange network releases all of its data for all of its sites under the Creative Commons license. It contains Stack Exchange site posts, comments, badges, links, history, votes, users, and tags, all as these files with one row per one record per row, and it's scrubbed of all personally identifying information. You can download it from the Internet Archive. It's a 21 gigabyte compressed zip file. For my demo, I am exclusively using just stackoverflow.com data, which comes to 90 gigabytes of uncompressed XML data. Out of that, I'm only using the post data, which comes out to a paltry 29 gigabytes. But it's just XML, so I mean, take that with a grain of salt. So it's not a huge data set, but for my limited computational resources, it does the trick. So the first demo is on a standalone machine. It's my multimedia machine at home, actually. This is the stats for it. I called it Hulk. It's a pretty beefy machine. It's actually getting a workout in this presentation, more so than it usually does. And I told my wife not to watch anything on it. I'll be running a Spark driver application on it. Although Spark has a lot of cluster support, you can easily just run it on a single machine, like what I'm about to do, and utilize all the cores and memory you have available. You can run Spark applications with a single library download and no other infrastructure to set up. So if you're used to the Hadoop world, it's a lot simpler to kind of get going than that craziness. Makes it easy to develop and troubleshoot Spark applications in isolation, and also makes it a lot easier to learn. So in the operation I'm going to show you, I'm going to count all the distinct tags that are associated with Stack Overflow questions that are tagged as Scala. So the people that worked at InMoment will probably get this, the co-occurring tags idea is what I'm trying to apply here. So let's all pray now. What's this? Nope. Okay, so this is going to go over the whole data set. I can show you the command later. And there's a ton of shit happening there, but I'll try and point to some of it. So in here it's saying this is the post XML file, and what it's doing is it's splitting it up into tiers, into chunks, and distributing it across all the different cores in my system. I'm trying to find the count here, but 53. Somewhere it should say how many, like it calculated how many, oh here it is, it's just over 2 lines. It's 78 of 913 chunks. So it's coordinating, it's doing a bunch of mapping operations. I'll show you the program in a second. Distributing them across eight worker processes. And they're all doing that work. So let me show you the app. So but I just have it on my local file system. I loaded it from my local file system, and I have a couple methods here just because I wanted to, in a later example, I'll be calling into them from the Scala REPL. So I apologize if it's a little hard to follow here. Sorry, just bear with me. Okay, so this questions section, I'm passing in a Spark context. I'm loading it from a text file. I'm filtering by row, and each row is an XML element. And I want to skip like the document element. So I'm only filtering for sections that have row in them. And this flat map operation is actually parsing the XML and getting out some key pieces of data for me. The type of post it is, it can be a question or an answer on Stack Overflow, the creation date, the tags, and I'm returning, in this case, just a single item list. And in the case that this blows up, I return nothing. So that's why I'm doing the flat map, because it's kind of a, I don't want this all to blow up if it can't actually parse anything. I'm doing a bunch of operations to format this data. It's all strings except for this ID. So I'm formatting the create date string here using just a simple date format from Java. I am parsing the tags here. So the tags look like this. It's a string like this. So I'm just doing some really crappy string manipulation there and putting it into a list. So every step of this data flow is kind of enriching the data a little bit more. And finally, for this method, I'm filtering just questions instead of answers. So this is saying only include questions in the data set. The questions is the method we were just in. To actually check if there's co-occurrence happening, it's a little hard to follow, but this is basically doing it. It's taking if it's a Scala question, get me all the other tags in it basically, and return this tuple here, which is basically a tag as the key in my tuple, and then like a seed value of 1. So when I get to my reduce step, I'm reducing by this key, which is a tag. So it's kind of like a group by operation. I probably could have done that actually. It would have been more readable. And then it's just summing all the instances of that tag. I'm doing I'm swapping things around to get to this step to have sorting, and I collect the operation. And finally, collect is like count. It kind of flushes the operation, and I just write it to local system in this case. So this is going to take a while to run. I'm not going to sit here and watch all these operations. Hopefully it'll be done by the end, but might not be. So let's get back to next example. Find my browser. So Spark on a cluster, is designed to run in a clustered environment. You can compile or download specific binaries of Spark that run on each of these supported environments. With the Spark standalone, you can set up a Spark cluster without any dependency on any other resource managers. So it's a pretty good solution if you're just playing around. This is probably the best solution for quick and dirty solutions. But if you want to build a cluster that other applications can run upon, like MapReduce, then it's a good idea to consider some of these other technologies that are more generalized in their clusters. So Hadoop Yarn specifically, yet another resource negotiator, I think is what it stands for. I didn't have much luck setting that up, to be honest, but I was able to sort of get it running. But I had a lot more success running it on Mesos, and the support isn't the best yet. I actually have some questions on their user list about how to submit jobs with it, but I can show an example in REPL using Mesos as a cluster. So just for people not familiar with Mesos, it's similar to Yarn, but it goes a step further in unifying a cluster into a single pool of resources that any application can use. Well, specifically especially designed applications. So the definition from their site is Apache Mesos abstracts CPU, memory, storage, and other compute resources away from the machines, physical or virtual, enabling fault-tolerant, elastic, distributed systems to easily be built and run effectively. I butchered that, sorry. So I'm going to show one last live demo. Again, it's on the stackoverflow.com data. I was really hoping to get the whole data set uploaded to, did I skip something? I didn't. I was hoping to get it into my cloud cluster, but the upload kept failing, and I'm just using my connection at home, which is restricted to 100K, and I made the mistake of just gzipping it first, and then it got corrupted, and I couldn't fix it. So I tried zip, but it's not finished yet. So unfortunately, I took a subset of the data, 1 million records, and I'll show you operations on that. So I chose to use the Google Cloud compute service because they have this amazing deal right now of, I don't know how long it's been around or how long it'll go on for, but you get $300 of credited to your account. You can use anything on Google Cloud Compute. There are some restrictions. For example, you can't have more than 8 virtual CPUs going, but you can slice that up. And the N1 standard 2 image is the largest VM you can set up. So if you don't have a Hulk laying around, then playing with a cluster setup is the next best thing. So I set up an Apache Mesos cluster with the help of a company called Mesosphere, and it's also a product actually. And Mesosphere, the definition from their site is a new kind of operating system that organizes all of your machines, VMs, cloud instances into a single pool of intelligently, dynamically shared resources. It runs on top and enhances any modern version of Linux. So Mesosphere has these really excellent guides to set up clusters on various infrastructure as a service providers, like Google Cloud Compute and Amazon Web Services, and one called DigitalOcean, which I hadn't heard of before. They even have, the coolest part is they even have these scripts that allow you to automate the setup of these environments if you provide them your access key. So a lot of the AWS, Google Cloud Compute, and I guess DigitalOcean too, they have an API where you can automate the setup of environments. You can turn them on. And they're aware of like this Google Cloud Compute deal. So they actually have a developer cluster you can spin up that works within the confines of that free tier they have. So it was really, really easy. I mean, all I had to do was accommodate my larger data set. Well, I guess I didn't because I didn't actually use it, but I just threw some extra disks on all of my nodes. So it basically looked like this. I have 1 master VM, 3 slave VMs for 4 in total. They had 2 CPUs each, 7.5 gigs of RAM each, and then HDFS. And I put that 500 gigabyte drive on each one of them. And this little snippet down here is just the those 4 nodes listening it through the Google Cloud API, the command line app. All right, here we go. Let's try and do something a little more interactive with the REPL. It finished. I'll show that later. All right. Something else. So I didn't actually type it out, but I've entered the Scala REPL here. I loaded my data set right here. So I have HDFS on this cluster. I created a small directory structure here with my posts, and I have this small subset with just 1 million records in it. And what I did here was I just got this ready to go. And let me paste some commands in here that will hopefully work. The first thing I'll do is get all the Scala questions. So these are questions that contain the tag Scala, and I'm going to cache this operation. So I'll do that. Nothing's actually happened yet. It hasn't actually executed a job. This is all just a stream right now. So if I want to get the count, this will flush the operation, and it'll talk to my the three nodes there. You can see how it's splitting up jobs in sets of 3, and hopefully this will finish before I stop talking. It shouldn't take too long. Anyways, once it's done, I want to show it'll spit out a number, just a count of questions that had Scala tags in them. And then I'll perform another operation on that cache data set. So I won't just sit here. I'll just move on to the next slide, and I'll come back to this in a second. But that's pretty much my presentation. I just wanted to talk about some of the resources that I use. So Spark documentation obviously is fantastic. It's really well done. This is the paper I was referring to throughout the talk. I highly recommend it. It's not completely accurate anymore. It was 4 years ago, but you should definitely check it out. And then, like I was saying earlier, Dean Wampler is a huge personality in this space, and he's done a bunch of talks on Apache Spark, and he pushed this project Spark Workshop to GitHub, and it has lots of examples and assignments for people to iterate through to learn more about Spark. So I highly recommend that. There's some resources on Cloudera. I mentioned all these things about the Google Cloud Compute, Mesosphere in the cloud. This is information on how to get that up and running. I didn't actually demo this slide, so there's some other information, but I forget what it is below the fold. Let me just see if this is done. It's done. So out of that million rows, only 252 questions were actually Scala, and the reason that's so low is because that subset is from the beginning of Stack Overflow, so back in 2008. So it does make it a very easy data set for me to work with here, because there's really not much going on. So let me perform that second operation I was talking about. Well, before I do that, let me just, so if I rerun this operation, it's going to be instantaneous, because close to, because it's all the memory. It is actually doing the work again, but over memory instead of sucking it up from HDFS. So in this other code snippet, I have another simple date format, and basically I want to get a time series data of when these questions were asked over using months as an interval. So this is using the same cached Scala queues data set, mapping over it. It's creating the simple date format and getting out specifically just year and month here. It's doing a count, sort of like what I was doing before, and sorting it and saving it actually into HDFS. Control D. There you go. It's done, and I can load it up. It's just HDFS command line. Where are you? There it is. So it ends up in as a directory in HDFS, split up into chunks, just like Hadoop does. And this get merge consolidates it into an actual text file for me. Yeah, and then you can see the output. So it's just the tuples really, and it starts to get bigger over time as you'd expect, and it kind of drops off here because I cut off data as part of my subset. That's just a simple example of how you can use the distributed caching to perform many operations on the same data set and take advantage of things actually being in memory. And if data sets are too large to be in memory, then they'll just be computed when you need that data. So it's very intelligent. Okay, almost done here. So that's it. I have this presentation and some of the sample code I was using, a bunch of other examples I didn't go over in a repository on GitHub. So I'm a software engineer working at Ethica, and we're hiring like everyone else. We're not using Spark in production, but we have lots of interesting data problems to solve, and maybe this will be applicable someday, I hope. And yeah, these are my details you can reach me at. And that's it.
Resource management. So, I mean, I think you did a great job of showing sort of the niceties of processing. But usually the part that's a lot less fun is getting it all up and running. So yeah. You mentioned sort of the facility with which you can go from sandbox to production-like environment in terms of resource management. Can you talk a little bit about what that involves in terms of configuration, both in terms of use of core and use of
what?
Use of CPU core in the the farming of jobs and plugging in particular.
I'll be honest, like that goes a little beyond scope. What I've learned, a lot of this, like Mesosphere, just kind of set it up for me. But yeah, there's lots of concerns once you get to actual cluster environments. I mean, the reduced steps to actually recombine the data, you can get a significant performance hits because of the shuffle over the network. In the Google Cloud Compute example, it's particularly noticeable because they're not all in the same availability zone and stuff. So there's a lot of thinking that goes into configuring a cluster like that.
But I mean, I guess my question was out of the box. It does a reasonable default. Right?
Yeah, the Spark standalone it has its own internal resource negotiator, and you define a master. You can define, I think, a backup master. I might be wrong, and then a bunch of slaves. And you just point when you do like a Spark submit, and you actually deploy a job. You just tell it. You use this cluster. This is my master. I can tell you the rest of the information you need to know about my cluster, and then you can do, depending on the cluster technology you're using, they support different configuration that you can throw at it to say, hey, use all the cores if you can. Yarn is particularly good at actually managing resources because a lot of jobs can be run on it. It has the security concerns built into it, so on the file system as well as who can really utilize all the resources on that cluster. So Yarn has lots of options there. I don't know so much about Mesos, how many options it has, but yeah, it really depends on the cluster technology you choose. If you have some relatively simple needs, then almost any of them will work for you. But Yarn seems to be the most evolved one from my learnings. Any other questions? No?
I'll steal the spot again. I mean, you showed the right, which I think was interesting. I mean, anytime you're engineering across an in-memory cluster, you worry about resilience, even over and above the promise. Does cache have a corresponding flush, or are you always obligated to sort of to explicitly write?
Like the cache operation, are you asking, does it like flush to disk or anything like
Well,
that?
I mean, the latency that's introduced with the HDFS approach is in part because of the desire for replay for your intermediate, reduce and collect. So what I'm wondering is if there's sort of within the API where there's the ability to say I've gotten to this point, and I actually now I just would like to just flush that cache because I'm not particularly interested in the real time after that point, but I am interested.
Get rid of it or persist it?
Persistent.
Yeah. Well, you can explicitly persist it anytime you want. I don't know if you can evict things from the cache. I assume you probably can, but generally it handles all that for you, pushes things out of the distributed memory if you need to.
But as you've seen it, the work of writing to disk is something that you have to take on explicitly as desired.
Yeah. From what I've seen.
There is an option to automatically serialize. You can choose your serialization framework.
Okay.
And stuff like that.
Mm-hmm.
But as a fault tolerant sort of.
You can checkpoint. There's a checkpoint in
That's
the RED.
that's what I'm getting at. Okay.
Cool. All right. Well, I guess that's it. Thanks for listening to me. I usually do a license giveaway, but I haven't set it up. I usually plug in everyone's name into a small scale app and do a draw for an IntelliJ license. I will do that, but I'll do it at home. And one of you will get that license. So yeah, thanks for coming out. Thanks for coming out. There's Polish pizza. There's a couple more beers. I'm gonna stick around for an hour or so, and yeah, just have fun, play ping pong. Thank you.
And a good crowd too.
Yeah. This is a really intelligent, respectful crowd that I like.
I mean, the rule of thumb is no live demo.
I know.
You did too. You did too.
I know. Yes.
I knew Andre Edelbrock, Keith Johnson, and Trevor Clark about 10 years ago. I worked with them at Crypto. So when you see them, tell them Angelo said hello.
Angelo, I'm a colleague also and a friend of Mike Straczynski, who's also.
Oh, there you go. Yeah.
Who's also in
I worked with Start. Oh,
Andrea and those guys are all my buddies.
there you go. Yeah, I worked with them back in Crypto. Andre was the product manager. We worked together quite a bit. Less with Trevor and more with Andre and Keegan. Actually, in the
Come up and visit us.